I will start. Give me one moment of organization for the class. I think I've changed my perspective on the projects. I designed a project in the syllabus before I met you that said, you should take a data set and do advanced time series analysis using R, and I want to report such and such a way. And now I've met you, and except for Charlie, you're statisticians, and I'm realizing that maybe that I'm not against that kind of report, that kind of project, but I think I'd like to say that if you wanted to do a more mathematical one, but very relevant to the course, okay. So for example, comparing and analyzing two different periodicity methods for irregular spacing, or a couple methods that the astronomers developed years ago, but no one's really looked at, or three different R-based implementations of wavelet decompositions for time series, and to say, well, the Stanford toolbox is this and the other toolbox is that. I could imagine a little more flexibility. Okay, you too. Even you could be more flexible. And all I would like to say is, soon I'm going to come to you and say, well, are you developing a project idea? And each one of us will have a brief conversation once or twice. And it sounds like a great project, and then end of the semester, you hand it in. Does that sound better, to have a little more flexibility than I stated in the syllabus? That suits your personal educational approach and not my preconceptions of you, which is what it did. Okay, that's only relevant to the legal students who are taking the class pass-fail, but it is a graduate course at 3 universities, and we have a responsibility to your education to make a good course. Well, one of the pleasures of this is that I'm not giving the whole course. We have these visiting speakers, and Ashish Mahabal from Caltech is a leader in exactly what his title is, of wide field astronomical surveys. And so I would sort of guess to say that Ashish and his colleagues, immediate colleagues, have more hands-on experience than anyone in the world that I can think of in these handling these large surveys. And one might say, well, it's an obscure backwater, it's nice, he's doing it. Oh no, he's the pioneer of LSST, the billion-dollar national project of astronomy for the 2020s. And everything that Caltech and others are working on now for the prototypes, these initial surveys, are all going to be needed not by a couple of dozen specialists, but they're going to be needed by thousands of astronomers, all from all universities and all walks of life, who are going to use LSST data. So what we're hearing then is the kind of things that underlie why SAMC is having a research project, and this topic is in fact one of the central issues of the SAMC research effort. Okay, Ashish, welcome, and we look forward.
Thank you, Eric, for the introduction. Eric, of course, overstates things a little bit. LSST is a huge project. It has many working groups and many people working on it. So I am one of the co-chairs of the transients and variables group. So still I've been involved right early on the start. And the thing that I do is that I am at the Center for Data-Driven Discovery at Caltech. And we have, in fact, been working on large surveys for almost, 17, 18 years now. And so we have been part of almost all the surveys, more or less, that have been happening. And so that part was definitely not exaggerated. Thank you, Eric. And so given the combination of the class, what I'm going to do is that initially I'm going to introduce a little bit more of the astronomy part for the large surveys, and then we'll go on to some of the methods that we have been using for the irregular time series. So what I'm showing here, for instance, would seem like, okay, we call light curves, or light curves are the name that we use for time series. And so I may use the two words interchangeably. And so we have light curves here for several different kinds of objects. And these light curves are not really light curves in the sense that these are folded light curves. So this is not how we observed them, but we figured out the period for them and then folded them along the period so that we get a nice curve. When the time series was in its original form, it was very, very sparse. And it's those kind of time series that I'll be talking about. For instance, what you see here is a phase, just 2 periods of the light curve. But the original data is from over 10 years. And over 10 years, the number of points we have is only about a couple hundred or so. So it's really, really sparse. And each point covers only about 30 seconds or so. So we'll come to that a little bit soon. So what I'm going to do is that we'll have a quick summary of what I'm going to cover later on, then a little bit of background domain knowledge. Then we'll come to the statistical features and priors. That is the main way we approach the light curves. Rather than dealing with the light curves themselves as objects, we convert them into something that is more manageable and work on them. And some of the things that are happening right now and in the near future that we'll come to. And maybe we'll look at some examples and exercises. These won't be compulsory, but it will be good if you can take a look at them and do something about them. Most of them will be R-based, but I also work a lot using Python. And I'm not going to state anything in Python today, but there are parallels that are happening within Python because that. So many of the things that we do, there's a lot of machine learning aspects that come to it because of the sheer size of the data sets that we have. So if you did not read it, we have of the order of several 100 million light curves. So that many rows in a catalog and tens to hundreds of columns in the catalogs. That's the typical thing that we have, and that's going to keep growing. Okay, so the quick summary. Again, time series and light curves, those are the synonyms that we'll be using. This is a typical light curve that we have. On the x-axis, we have days, and we see about 1200 days here. And on the y-axis is magnitude. I'm sure you have been told about this before, but we'll go through it again. Magnitude is logarithmic inverse of flux. So smaller numbers are brighter, and larger numbers are fainter. So when you see it shown like this, then that is the correct way astronomers would show it. And 1 magnitude is about 2.5 times in flux. So if you see a change of 1 magnitude, it is roughly 2.5. If you see a change of 5 magnitudes, it is 100 times difference. So magnitude 15 would be 100 times brighter than magnitude 20. And with the visible eye, you can see roughly up to 6th magnitude stars at night. So we have these variations that you can see, and as you can see, this is about 4 years or so, several points there. And we do have a large number of upper limits. So there are objects which we do not detect. So we are observing a particular part of the sky, and later observations indicate to us that there is something there or there should have been something there. But when we were observing, we had not seen anything there. What that means is that there is a certain upper limit that we can reach with our survey, and this tends to be variable for various reasons. We'll come to that a little bit. It could be because of the phase of the moon, because of how weather is, if there are a few clouds here and there, and so on. So that tends to be variable, and all we can say is that if the object was in fact there, it was at most as bright as this at that particular epoch. And these are the 2 images that show that. So this is an image taken on one of these epochs, not necessarily this epoch, where we do not see anything, and later on there was something bright. So this could be a supernova, for instance. In fact, this one is. So there was nothing there. The background light for the galaxy was somewhere there, and then suddenly one of the star blew up. It became brighter by from about 20 to 16, so it became brighter by 100 times. And then it faded over a few days. And then we'll continue to follow that up in order to figure that out. Now, think of this, right? When you look at the sky, if you look at the stars, you don't see them changing. Our sun, for instance, we have been following it for a long time, and we see sunspots and so on, not with our eyes, of course, but there are small variations that happen. When there are solar flares, it affects the layers around the Earth, and it affects radio communication and so on. But those variations are really small, right? If the sun were to do something like this, well, not a supernova, of course, that will explode, but even a very tiny fraction of this, that won't be good for us. And what we are doing is that we are looking at a large number of stars and trying to figure out which stars do what and so on, right? So some of the surveys that we'll be using, I'll mention those initially. There are a large number of surveys, and I'll mention many of those, like there's CRTS, PanSTARRS, Gaia, PTF, ZTF is coming on, LSST will be coming on, and so on. So one of the surveys that I have been using for a long time is the Catalina Real-Time Transient Survey. Its parent survey is the Catalina Sky Survey, which is looking for asteroids especially asteroids that may come close to Earth. And there are a very large number of them. There are thousands which are greater than 1 kilometer, and all of them are potentially dangerous. So there are 2 telescopes that are currently continuing observations. There was a third one in the southern hemisphere. Both these are in the northern hemisphere. And we have for about 14 years of data already, and that's continuing. In fact, this year, both these telescopes got larger CCDs. They have now 10K by 10K CCDs. So that many points are being observed simultaneously, larger area, and so on. And then we reach up to about 20 magnitudes, a 20th magnitude, as faint as that typically. Both the telescopes are roughly 1 meter class. And again, this will become more perspective when we go to larger number, about 200 pointings in 30 seconds each. So again, think of this, right? 30 seconds, about 200 observations. That's about 100 minutes or about 2 hours. If there are more observations in a field, it will go to 3-4 hours. So think about this, that 1 year has roughly pi into 10 raised to 7 seconds. So 10 years will have pi into 10 raised to 8 seconds, right? And what we have in about 100 minutes is only about so many thousand seconds. So if this were the timeline, right? Think about what a small fraction of that timeline we are actually covering using our observations, right? It's negligible. So 100 minutes compared to 14 years or whatever. Now, what that does is that the sparsity of it, we can get an inkling of what the object is, but not necessarily how it's going to behave, what it was doing in between, and so on. But by looking at a large number of objects, we can start building priors. We can use physical models, and that is what we've been doing for a long time. So you'll hear the word transient several times from me because I work especially in transients. So let's quickly look at what a transient can be. CRTS, to look for asteroids, takes 4 images in succession, separated by about 10 minutes. Right? So you have one image, 10 minutes later, 10 minutes later, 10 minutes later. And you can see that there is an object at the center which is fading. The other objects are not changing much, right? They're fairly constant. And so this is the corresponding light curve for that. For many years, it's roughly constant, and then suddenly in a short time, you see it rising several magnitudes, becoming brighter. This is what we would be calling a transient. Now, a variable is another term that you will hear often. And a variable is an object that varies. So every transient is a variable, but many people will not call variables as transients. That is because the variables will keep going up and down, many of them in a periodic fashion. And that's another interesting aspect that we'll want to look for. Even if our time series are sparse, we'll want to figure out if they are periodic, because that's important. That's a small fraction of all objects that are periodic. We'll want to look at that. And so any large brightness change in the relatively small change in magnitude is what these objects will be. And so several years ago, this is the kind of configuration that you'll find looking for these objects. What you have are some priors that were built using light curves from the past and color information. Color information is simply information from 2 different filters. So if you have 2 different filters, the difference between those in magnitudes gives you a color. And then these are some event parameters that you get from observations. You feed those in, feed the priors in, get extra contextual information that comes in. NVO was the National Virtual Observatory that was formed several years ago. There was Virtual Astronomical Observatory after that, and right now there is an international organization called the IVOA that does some work of that kind. But what we want to do is that combine all this information in this black box, which can be made of several different pieces, and lead to a large number of probabilities of different classes. So typically, we don't want hard classification, which simply says that, yes, this is a supernova, that's it. It cannot be anything else, right? Because we know that given the information that we have, it's always possible that it's a supernova 99.9999%, and then there is a very small chance it's something else. And then so 99% is still good, but if it's more like 80-20 or 60-40, we're not in a good shape, we're not in a good region of the parameter space, and we definitely would want to go for additional observations to try to figure what that is, right? So this is how it was several years ago, and in terms of how the structure of the thing is, it hasn't changed much. There are more pieces that have been brought in, there are more bits and pieces, more data, and so on, but this is how things will keep looking for a long time. And so there's Eric mentioned LSST, and this is how LSST is going to look. So what LSST will be, it's an 8-meter telescope. It's not there yet. It'll start observations in 2022, so another few years. But the construction is already going on. I was there last month, and the telescope does look like how we have been showing in various schematics, so it's taking shape. What it is going to do is that it's going to be a very fast telescope. It's going to look at the entire southern sky again and again every few nights. And what we are going to have is 1,000 visits every night. And then the observations are going to be short. The data is going to be about 15 terabytes every night. The main thing is going to be this. There are going to be of the order of 10 million real-time events per night for 10 years. And by an event, I mean a transient or a variable that changes a lot. With the current surveys, it is of the order of about 10 per night. It's going to be 10 million. And this is where what we really need to do is get into the statistical arena, get into the machine learning arena, which has already been happening, of course, right? Right now, many of the things are done where humans can look at the few objects that look very interesting, decide what needs to be done, go and take follow-up. So with 10 million, humans won't be able to look at it. Not just that, but what's going to happen is that we'll have to figure out which ones are the rare objects and have follow-up capabilities only for a few objects. So even if there are a million out of those 10 million that are rare, it won't be, but if there are, we won't have enough follow-up capability to go after them and do anything about them, right? And so the total number of objects that we'll be seeing is 38 billion, 24 billion will be galaxies, so more galaxies than stars at the time. You'll see in the later picture that all the objects that you see at night typically are stars, right? Hardly any galaxies. And so this is how one of the, what is called a broker for LSST is going to look like. So this picture in philosophy is no different from the picture that I showed you earlier. It just has more bells and whistles, right? So we'll start with about 10⁻⁷ transients, and by the end of the night, there'll still be about 1,000 rare transients every night, and those are the ones that we need to. And the light curves, the time series with LSST are going to be as sparse as with CRTS. It's going to have about 1,000 observations in 10 years, but the 1,000 observations are going to be separated in 5 to 6 different filters. And so per filter, you are going to have about a couple hundred observations in 10 years, same as CRTS. CRTS, by the way, doesn't use filters. It has an open area, so it lets in light from all visible wavelengths. So now let's look at some background domain knowledge for all this quickly. So the reason we want to do all this is we want to understand the universe, and the way to do that is using classification. Classification tells us what different kinds of objects are. And so we start by broadly dividing the objects that we know about in terms of solar system objects. These tend to be moving objects. Stars in our galaxy, they do contain a small number of variables. All stars are variable at some level, but most are not variable in our lifetime and not by too much, right? And then they do have proper motion. So stars are mostly constant in position, but even in our lifetime or even in a couple of years, you do see a little bit of motion because all the galaxy is dynamic. And then there are extragalactic, mostly transient objects that we see varying. So this is how our solar system looks. This is the inner solar system. This is the orbit of Mars, and then there's the asteroid belt. There are millions of asteroids there. And then Jupiter. Every now and then, some of those asteroids get nudged either by Jupiter or by Mars towards us. And the solar system itself is huge, of course, and there are many objects that come towards us. So one reason we need to look for asteroids, many people are interested in asteroids inherently, so they want to look at asteroids for their own science. But even people in time domain surveys who are not interested in asteroids do want to look out and find asteroids because they want to first separate them, because since asteroids keep moving, they keep coming again and again in your fields. And if you have not cataloged them and removed them from your observations, you'll keep mistaking them for transients, other interesting objects, and so on in single pictures. The stars, there is a huge variety in them. I've shown here only two axes in what's called the Hertzsprung-Russell diagram. You've got surface temperature going on the x-axis. On the y-axis, you've got brightness. And what is shown here as blue or white or yellow or red, orange are like filters. So if you're looking at all the stars with the blue filter, these are the objects that will stand out. If you're using a red filter, objects on this side will stand out. If you're using both filters, then taking the difference between them is what is going to tell you more about those objects, what those are, and so on. So when you take time series of large number of objects, right? If you have multiple filters, that is going to be helpful to you in trying to figure out what classes they belong to. Then when one goes to transient objects or other extragalactic objects, then here what we have is the time scale in days of their variability. And so this is the area where we can easily follow. When a transient goes off, then I need some time normally to go to another telescope and start observing, get the data and so on. If I needed only minutes or seconds, and we already have those capabilities for in a limited cases, then we'll be able to cover this area. And to be able to cover this area, we need even faster lookups, right? Instant lookups. And then we need to be able to build populations of those to get to these events, like say the tidal disruption events. We have a few plausible examples for that, but we'll be getting into very large number of cases very soon. So what we really need to get to is a classification tree of this kind. And what we have here, for instance, is there is extrinsic variability. Variability not because of something happening inside the object, but because there is an eclipse, for instance, or just plain motion, right? So asteroids, you can have eclipses or rotations. In stars, you can have eclipses or rotations or microlensing, and all those phenomena are known. Or intrinsic variability, where actually something is happening inside the object itself. So you have stars where there are eruptions happening, and then there are pulsations happening. In AGN, these are active galactic nuclei. So that the center of the galaxy, there is a black hole, and it's accreting material, and there are jets coming out. There is a lot of magnetic activity happening and all that. So this is, again, a small subset of all the different subclasses that are possible for variable objects. The actual set of variable classes is far, far larger. Many of them have subsets. Here, for instance, for supernovae, we have only a few classes that are mentioned, and for RR Lyrae, there aren't any mentioned. So just for RR Lyrae, there are various subclasses and so on, right? And so these variability tends to be of various different types also. So if you look at pulsations or white dwarfs, it is on the order of 4 to 10 minutes. And then the amplitude is typically very small, 0.1 magnitude. And that is going to be one of our measures to look at what the variability is. So the measurements that we'll be doing, depending on how good your instrument is, you'll be able to look at 0.1 magnitude variations or less than that. But there will be other objects where the variability is more. So those are likely to overwhelm if there are enough numbers of those. So you can see that there are all kinds of time scales and all kinds of amplitudes that you see. And similarly, the expected rate of transients, those also vary a lot. This is with LSST again. So with LSST, every year we expect to find about 20,000 luminous supernovae. So the rates are simply going to be huge with the surveys that are coming later on, right? So these are the broad areas of objects that we have quickly gone through. And how do we look for them? If one can take a spectrum of an object, that's a very good thing, because that immediately tells you what elements are in that source, what the brightness is at different wavelengths and so on. But taking a spectrum is very expensive. So we do not have, it's just not going to be possible to get spectra for everything in the near future. So the next thing that we can do is take colors and time series. And that is what then gives us characterization and possibly unsupervised clustering that we can do with those. And there are other modes that we won't be going into. So this is how some of the filters look. In the visible range, we go from about 300 nanometers to 1,000 nanometers. And these are the LSST filters, U, G, R, I, Z, and Y. LSST filters wheel has only 5 slots, so 5 of them will be in at a time. And then this shows 2 colors. This is the old picture from the DePauw plates, the G minus R and R minus I. So you take observations in the G band and the R band and the R band and the I band and take the difference in those magnitudes. And all the stars in our galaxy will occupy this area, where there are some quasars that will occupy this area. And when you take a spectrum, you can differentiate between them easily. So the type 2 quasars are shown here, and the high Z quasars are shown here, for instance, right? And so if you take a spectrum, great, but it's expensive. You cannot do that. You need to have time series or colors to do that. And colors, again, you could have, say, 100 points in G and 100 in R, or 200 in 1, depending on what kind of problem that you are going after. And that is where what we have is a large number of surveys which have different science goals. So this is CRTS. which is going after asteroids. It doesn't use any filters, all the visible range, all the photons coming together, 4 quick observations, the next set of 4 observations could be the next night, a month later, or a week later, and so on. PTF, which uses only 2 filters. Again, both of these are, so CRTS had 3 telescopes, so 2 of them did the north and 1 did the south. PTF has 1 telescope which does the north. Gaia is space-based. Its scientific goal is astrometry, that is position. It's far, far more accurate than by orders of magnitude than what we have had so far. But it's going to do a total of 70 observations in 5 years. But it also has low resolution spectrum for most objects. So that's going to be very, very good for position. So it's going to allow us to look for streams of different kinds of objects, other galaxies that we have been interacting with our galaxies and so on. And LSST, this is built through a simulator. LSST is not there, as I said, but it's going to cover the entire southern hemisphere a large number of times. So to summarize, what do surveys do? They pick low-hanging fruit. Because they're so sparse and they're built with specific science capabilities in mind, they try to go after those and try to do those well, right? So they would select best possible objects and easy science. I say easy, it's not easy, but only because they do a good job of whatever they're doing, whatever they built for, they do that. And the other parts they may want to leave. And they try to get spectroscopy to confirm theories, to try to push our boundaries as far as we can. So that does push the envelope, but also leaves large number of gaps as well, right? Remember again that this is the kind of thing that we have. So small number of observations, short observations over a long period. Let's quickly look at how gaps can be misleading. This is a time series not from astronomy now, but this Oracle opening prizes stock market, right? And so if you look at something like this, you could just put a straight line through it. But what is not mentioned in the diagram on the left-hand side is that the stock market doesn't open on weekends. And so if you leave the Saturday, Sunday part out of those and just connect Monday to Friday, this is the kind of things that you see. So typically in a week you see that there are trends, and typically the trend would be going up or going down most of the times. And even that is not a complete picture, because for one day still you have a single point. And the stock market was closed during the night. So when the stock market was closed, on the other side of the globe where other stock markets were open, there may have been a calamity, there may have been an earthquake, or there was a coup, or there was an alliance. So those things change things a lot, and we don't know what was happening. And something similar applies also to astronomy. When you have large gaps, you cannot guess what was happening. You cannot just interpolate between those 2 points what's happening. There are interpolation methods that you can try to use. For instance, you could have good Gaussian methods where you try to increase the error bar between those two and try to make your best case. But that's the kind of thing that we have here, and the same applies for astronomy too. So let's quickly look at some of the surveys and how their observations and their gaps are, right? So these are DPOS plates, Digitized Palomar Observatory Sky Survey. That was the last survey that was done with photographic plates. That was before the charge-coupled devices came on all the telescopes, which are far more versatile, better electronics and all that. So there we had 3 different filters or emulsions, the J, F, and N. And the entire northern sky was covered by this. Each plate was about 6.5 degree by 6.5 degree. Compared to that, the size of the moon, which is only about 0.5 degrees in diameter. So the moon will fit in a corner of the DPOS plates. And the centers of the DPOS plates were separated by 5 degrees, which means that there was somewhat of an overlap between adjacent plates. And the adjacent plates or the different filters at the same location may have been taken. Each of the observation, by the way, was 1 hour long. So the photographic plate would be put for 1 hour, there would be an exposure, you take it out, put another plate, move the telescope, right? And so the successive plates, the difference between them in time could be as short as 1 hour, or it could be as long as 15 years. So here we see an example where at this location there is a bright object suddenly in N filter. This was taken in 1990, 1997, 1988. So you don't know what the object was doing in between. And all you had were these 6 points. So some of the prior gathering that we started was with this sparse data. So all we had is at most 6 points for a fraction of the sky. and only 3 points for everything else. And 3 points, of course, were all in different filters, so it was not really a time series, but we had time series of 6 points and so on. And using that, we built some initial priors and started estimating how many objects of different kinds we could find. If you look at if you look at other surveys, CRTS, for instance, as I mentioned, again, we have days here. This is about 3,000 days that are shown about 10 years, and all these points. So these gaps in between, right? This is a typical light curve that we have for CRTS objects. Those gaps are when that object is in the direction of the sun. So this Earth is going around the sun. So there are several months when you cannot see an object in optical. Radio doesn't have that kind of problems, but in optical we do. Compared to that, some other time series that we have, this is a Kepler time series, and we are looking at a short part there, so only 100 days, and it seems almost continuous compared to that. So when we had at most a few points there, we have a few thousand points here. And about Kepler and exoplanet search, we'll have 2 separate talks later on, I think the next week and the week after, and they will be covering a lot more about the methods that can be used at the time. So Kepler is a small area and non-sparse. Here is an example of Kepler time series though, and even there things can look very different. So if you look at small intervals at different times, those time series can look very different from each other. And so if you had access to only that time series and you were trying to say what that object is, it's not necessary that you will be right all the time. Right? From that behavior, if it is very characteristic of that kind of object, yes. But there may be overlaps, there may be variations that you may not be aware of. Okay, so we have already seen that what we measure the flux in is magnitudes, which is inverse logarithmic. The other thing that I wanted to point out is that what we measure time is in typically days, so that is the unit that you'll often find. And all the light curves time series you'll typically have 3 columns. There will be time, variation, and error, which will be the MJDs, max, and mag errors. The MJD is the modified Julian day, and it's interesting to go into that history. We won't do that today, but you should look that up, because there's a complexity of what different units get mixed in and so on. So it's not exactly Julian, it's not exactly Gregorian, and it uses a combination of various things and so on to get into that. But what I wanted to say is that even if astronomers use these strange terms, strange units, what is done is that the measurements are very meticulous. So forgetting about the units themselves, the errors are well measured, and all the other computations that are done, astronomers tend to be very careful. And that is why, in fact, there's a lot of learning that's happening from other fields are learning from astronomers in terms of methodology and so on. The other thing you have to remember is that the Julian day and MJD are off by half a day. So many times when you are doing computation, that's something that will become important to keep in mind. So looking at these then, we saw that DPOS has large area and serendipitous overlap. Kepler has non-sparse and small area. CRTS open filter but lumpy cadence because of asteroids. And other surveys like PTF, PAN-STARRS, Gaia, and in future LSST and ZTF will be multi-filter, and they will have mixed cadence because they'll be going after multiple science issues. Also SK and radio, we won't be going into that. There are slightly different methodologies that are used there, and pulsar timing arrays, we won't be going into that. I don't know if there's going to be a talk related to that, maybe, or in this.
Not in this class.
Okay, right. Okay, so let's quickly summarize what a typical light curve will look like. This is our light curve. Not so many upper limits in a typical light curve, but we'll have a few examples of those. The blue points are the ones where actual observations have happened. So we have large gaps. Again, these are the annual gaps, and even within a particular period when it can be observed, there are gaps. They are very irregular, and there are the error bars on each of them also vary. And the reasons for all those 3 things are given here. They are heteroscedastic because of weather, because of moon, because of varying air mass. You may be looking today at that object here, but tomorrow when you do observe the same object, it may be at some other point. So large amount of mass of the air coming in. They're irregular because the science objectives differ. Again, weather and moon can also affect things. So you may want to observe it with every hour, for instance, but then the sun rises and you cannot do anything about that. Or there are again large gaps because of things can be expensive. You cannot observe everything all the time, and so on, right? So those are our boundary conditions. So what is it that we can do with all these gappy, heteroscedastic, and irregular light curves? You try to change your problem, right? If you want to catch a lion, one way to do that is enter the cage. Or, well, you try to modify the beast to tame it in certain ways. So what you try to do is that you can abstract the light curves and obtain generic statistical measures for them. And it is that space in which we tend to operate mostly, rather than dealing with the light curves as individual objects all the time. You convert them into a small number of numbers and deal with them. The other thing that you want to do is that use domain knowledge to look for specific characteristics. So when you talk of statistical characteristics, what comes to mind are typical moments, means and medians and skew and kurtosis. Those are standard. But given your knowledge that a particular astronomical object is likely to show such and such behavior, you can use that to characterize the time series and use that as an additional feature in your data set. And periodicity is again another important thing. We know many reasons why objects tend to be periodic. They can be pulsating, they can be rotating, and there can be, say, binary objects going around each other that gives rise to periods. So finding periodicity is a big thing. We'll be touching upon it. We won't go into great detail about finding periods, but that's a big problem. Again, because the time series are very sparse. If you have a continuous time series, then that's not too difficult, right? So I was talking to Eric earlier about this DTW clust package in R. I haven't used that, which is used for more, it uses time warping to look for similarity between light curves. So some of you may want to explore that with some of the time series that are not as sparse as the sparsest ones that I've shown. So keep that in mind. Similarity measures, direct light curves, that may be one way of looking at things also. So what do we mean by getting statistical features? So we have light curves of this kind. These are our time series. And we try to abstract them into features like amplitudes or moments, periodicity, etc., so that we get feature vectors for every object. So this is one row in my catalog. And then I try to convert that row into a set of numbers. And then for every row, I have the same or similar set of numbers. Then each of those columns becomes my vector. So each of those columns becomes a new dimension for me. And then instead of working in this dimension, I start working in those dimensions. 3 dimensions are shown here, so I can try to do clustering in that or apply all kinds of other statistical, mathematical, and machine learning methods that I want to on that particular thing. So here is an example. Again, this is a folded light curve, and I'm showing 2 features. Here, the period. So we are showing phase 0 to 2. And then this is the amplitude. So amplitude sometimes is defined as half the difference between max to min, but sometimes also max to min. So you have to be careful who's defining things how. And then you have the mean and the median. So these are 4 very standard ones that are shown here for a single light curve. But there can be more, and you can put all of those. So here is an example of a few more. So you can have skew and standard deviation, and what fraction of points are beyond one standard deviation, or the Stetson J and K variables, what's the slope of the light curve in general trend, or the amplitude, and so on. And then we have a light curve characterization service at Caltech. You can take a look at it. It is not industrial. You cannot put million light curves there, but for a small set of light curves, you can get a large number of such features back from the service. And there is description of the large number that we use there, and we'll be seeing a few. So instead of, yeah.
So when you're calculating these features, are you often ignoring the measurement error, or?
Very good point. So there are many features or many computations that do not take into consideration the errors, unfortunately. We'd like them to do that, but not all statistical features take that into consideration. Because we have good errors, we have error measurements, so it'll be very good if we have corresponding ones. Unfortunately, there aren't enough that do that. So just like we overplotted a few features here, we can overplot all of them, and this is the kind of thing that we'll look. And this is also only a subset of what we have. And again, not all features can really be shown in a simple way in this fashion.
As a follow-up to David's excellent question, this was my question. true. But that a lot of the methods wouldn't know how to use that even if you had. And that's a great area of research.
Absolutely.
Is
Yeah.
suppose that you could calculate a feature likelihood function instead of point. How would you use it to do classification?
Okay, so we'll come to classification later on, and that's where some of the fuzziness can come in, and about the soft classification where we can have some leeway around a particular classification that we come to. Yes, so definitely if we have newer methods or modified methods of the existing methods which can incorporate error bars, that will be fantastic and astronomers will love it. So here is an example of some of the Stetson numbers that we have. So I was calculated initially, which was pairwise observations in 2 different filters. So suppose you have time series in 2 different filters. What you do is that you take them pairwise. You also take the mean values of both the time series, and you figure out for each of these pairs how different they are from the mean. So if they are different from the mean, these numbers are going to be larger. And if they're close to the mean, these numbers are going to be small. So that is all that I is doing. It's simply trying to figure out how different individual points in the 2 filters are different from the typical mean value. Now J takes that one step forward, and without wanting you to have 2 separate filters, it uses a single time series and takes observations pairwise. So that is what is in these pairs here. And what it is simply asking is that if I take these pairwise observations, how different are they from the mean? So if it's looking at the residuals essentially when considering pairwise. And so what's happening there is that if there are variations from the mean, then that value will go up, value of J. And then K is another slight variation on that, where the pairing requirement is removed. So for each individual point, one is trying to figure out how different it is from the underlying distribution. It turns out that for Gaussian distributions, K is about 0.798. And if the distributions are smoother than that, it is higher than that up to 1. But if it is less smooth, that is if it is more erratic, the value is lower than 0.798. Therefore, if you take K divided by 0.798 and multiply them with J, you get another parameter that you can use. And we have found that J has been very useful to look for variable objects. So I mentioned that all stars are variable to some level, but most stars within our lifetime, the way we observe them, they don't seem variable at all. And parameters like these bear that out. So only about 3% or so stars are variable within our observational combinations. Okay, here are the numbers actually. So for the CRTS, we looked at all the northern objects, about 150 million, and about 5.5 million of them turned to be variables after filtering through this particular filter J. And then you do additional things like Loam-Scargill fit to them, and then additional thresholds on other features and so on. And so you are left with about 50,000 periodic variables.
Yeah.
Is there something you could say briefly about how you set a threshold for J? Is that something that's kind of built into J?
No. So in fact, we had to do it iteratively. So what happens with CRTS is that there are a large number of areas of the sky where we go again and again. So those we call as our fields. And so per field, we calculated it differently by looking at the distribution of J. And that is mainly because there are variations in observations, the moon phase, weather, and so on, which we needed to take into consideration. So it is not a particular hard threshold that you can use, but you do it a little bit iteratively. And so these 50,000 variables, we have a data set for that. If some of you are interested in using that, that'll be a great thing. There are about 15 classes in there. And this Loam-Scargill that I mentioned, let's quickly take a look at that. So what it does is it's essentially, you take many sines and cosines, and it's a least squares way of minimizing that. The thing that you have to keep in mind is that the number of points that you have should not, that number should not be exceeded by the number of sines and cosines that you are using during the fit. And the original version used mean equal to 0 by, say, subtracting out the mean, but there is a generalized version that can be used where you don't have to take that into consideration. And there are other variations that it's also known by some other names, like the least square spectral analysis. Yesterday I also found this name, matching pursuit. I'm not exactly sure of that, but that's another name that's for a closely allied topic that is used. So that's one thing that is used for period finding typically. And for the exoplanet talks, you'll hear of other methods that have been used specifically for exoplanet period finding, because there you can find eclipses, which is one of the main things that they're doing. Or one can also look for entropy-based methods when one wants to go after the period. So what is being done here is that you have to consider a large number of different possible times, and then you fold the light curve at those times. And then once you have done that, your phase from 0 to 1, you divide it into large number of partitions. And then in those large number of partitions, you count how many points you have. And then that gives you your entropy. Now this, if you do it just plainly like that, you find that there is an alias for 1 day. Because again, what happens is that, and that's slightly a quirk of astronomy or astronomical observations, which we have been trying to avoid, but you cannot completely avoid it. What happens is that if an object is near the zenith, or if it's crossing, this is east and this is west, and so this is how all the objects seem to go. And if you observe them in this area, then the air mass is the least for them. So that is when you are likely to get the best observing, right? But if you keep on observing always at zenith, then what's going to happen is that a false period of about a day is going to be introduced in your time series. If you are ignoring any variations that are there, just because you are observing it again and again there, and if you ask any standard method to get a period of that, you'll find that there is large power there. So one thing that is done in many surveys is that you try to have a little bit of spread in the air mass, so it's spread out there. The other thing that you can do is that do your partitions not only in the phase, but also in the magnitude, especially if you're looking at variable objects. So instead of having just one-dimensional partitions, you have now two-dimensional partitions. And once you start counting your counts in each of those bins, then you get a better entropy and you can figure out what the variables
So
are.
that aliasing issue is unique to the entropy method, right?
No, it's a generic. Yeah, it is a generic.
generic.
Yeah.
So it's, I don't know, maybe worth mentioning for statisticians, but you can view these kinds of methods as an approximation to a Dirichlet binomial Bayesian piecewise constant model. The entropy pops out as kind of an approximation for how you, the map estimator and that kind of
So then the other thing that you can do is start defining specific features or specific parameters that you think come from the science, and see how they can start dividing your domain into different parts. So here there's a parameter Q that has been defined. What it's looking for is that if you know that the variation is roughly periodic, but the amplitude is not constant at those different periods, then whether you can catch that, because different physical phenomena can lead to something like that. So what you're simply doing is that you're trying to figure out the residual, and you're looking at comparing that with the raw values that you have. So when you have a smooth variation where the amplitudes are also constant, then the numerator is going to be small. And so you're going to have a small Q value. Whereas here, when you go to the extreme values like say 0.7 that you see here, the ups and downs are roughly periodic, but the amplitudes are wildly differing. And so what you have there is, compared to that case of Q equal to 0, the numerator is larger, and that is what reflects in the Q parameter. And so that will allow you to separate how the behavior of the object is with a single parameter. Or you can define something else like M, which is burster or dipper. Here what you're doing is that you're looking at 10 percentile values, the faintest or the brightest ones, and comparing that with the median value. And when you do that, the objects that have more outbursts will have a negative value of M, whereas objects that have more dips, this could be because of eclipsing or absorption or whatever, you'll have a positive value of M. and the others will be in between. So again, you have a variation that single parameter can bring to you. And then if you do a Q versus M plot and have large number of different already classified objects put on that, you can see how you can start separating them to an extent. And these light curves that I showed you, by the way, were not sparse. They were not ultra dense, but they were not sparse either. So as you start going to sparser light curves, getting Q and M or features like those reliably may not always be possible. So you have to keep that in mind. But it is features like these that you can define specifically. And so what you have is a large number of features that become available to you, right? So there can be many contextual features as well. Distance to the nearest star, that becomes an important feature, though it is not intrinsic to the object itself. And that is because if you do have a star nearby, then depending on what kind of star it is, you can say whether what you saw going off as a transient was a supernova or not, if it was a radio object, whether it was an extragalactic object bright in the radio, and so on. So the magnitude of the star tells you a lot also, whether it's faint or bright. That's another thing that happens many times in statistics if you don't pay attention to the domain knowledge. If statisticians are given a data set and asked to find out 2 clusters in them, one of the simplest cluster they often come up which is separated by magnitude, which is not the main thing that we are looking at because there can be multiple populations within that and so on. So then distance nearest radio source, we can have follow-up characterizations from various light curves. These we already saw. So what starts happening is that at some point there is a redundancy in these. Not all of these are independent from each other. So you are now building this new table which has tens of features, and the actual dimensionality of your space is not that high. So what you need to do is that go to some method which will allow you to do reduction of those dimensions. So you'll have to do some feature selection strategy, and there are many ways of doing that. So you're now trying to arrange things by how important something is, and there again you have to make sure that you are not incorporating some of the values that are trivial. For instance, the number of points in the light curve, that itself can make it more important, but that's something that you don't want. There are many different methods that you can use. And that is where another important thing comes in. When you want to decide which features are important, you have to ask a specific question, and with respect to that question, then your second question becomes valid. If I'm trying to separate W UMA type from Myra, then the set of features that are important can be completely different from when I'm trying to classify supernovae versus AGN, or CVs versus AGNs, and so on. So in some sense, you can try to do a generic search for the most important features, but in most cases you cannot. You have to keep that in mind. So whatever feature set that you use, you have to make do with that. So here's an example of separating RR Lyrae from W UMA stars. So this is a kind of eclipsing binary, contact binary, whereas RR Lyrae are pulsating stars. Both show periodic variations, and when you look at various features, you may or may not be able to read this, but with that specific separation in mind, then if you ask the question which features are important, you get back an answer, and indeed when you use those features, you do see that there is a reasonably good separation in those two spaces. This is not one of the most difficult problems, but this is how you can go about, and that is where what one comes to is some kind of hierarchical classification. So rather than trying to classify all types of objects at once, you can start to break the big problem into smaller problems and try to get into that. So there are a variety of parameters, and we need to choose judiciously from them. So there are whole curve measures like median and mean and so on, but there can also be fitted curve measures, like you can have scale total variation, or you can also have residuals from fit measures. So once you have done a fit to whatever curve that you have, if you remove that, you get residuals, and those residuals can become useful parameters too. Or you can have cluster measures where you are fitting clusters. So I told you that CRTS observations, we take 4 observations within 30 minutes, and the next cluster can be some other time. Now, depending on your method, it may be worth simply taking the average of the first 4 magnitudes and the average of the next 4 and doing a fit to that. If you're looking for variability at very short time scale, you may not want to do that. But if you don't care about short-term variability because you know that your objects vary on a somewhat longer time scale, you may want to combine them together and so on. So from here, what we do is that we can go on to hierarchical approach to classification. So maybe what we'll do is that in a couple of minutes, we'll take a short break and come back in 10 more minutes. But this is what one can do. So we can break the big problem into smaller problems. If you look at a supernova, then that was one of the first light curves that I showed you where things are quiescent, you don't see anything. Suddenly something becomes bright by 5 magnitudes and fades in a time of few weeks or so, right? So separating those from other variability is far simpler. So that is the first problem that one could take up, separate simply supernova from non-supernova. You can easily get to close to 100% separation for that. And then for the ones which are supernova, then there are many subclasses. So the classification accuracy can start going down depending on how many
So for
features
just
you
the
have.
accuracy numbers you're quoting for how much of the light curve?
Good question. So in this case, this was done where we used the entire light curve, and then we made sure that the part where the quiescent part was, the program took care of that. And these can be different methods, by the way. It doesn't have to be the same method that's doing that. So it was tuned to that. But how many points did we have? We had several tens of points at least for that. Yeah. And then as you can see, the accuracy can start going there. Here it's already at 86%. And then there are the CVs and blazars. These are both stochastic processes. And so it's connected to each other over very long term. You have to keep that in mind. And then there are periodic ones like RR Lyrae and Myra. Myra are very long term variables and so on. So when you start going into that, you can have more branches for each of them for different kinds of periodicity and so on. So let's take a quick break and come back after the break.
Okay, let's start. Let's start with comments and questions.
I have a pretty general question. Like when you're collecting data, like say every night, and you're collecting like tons of data, then when you model this, do you do a kind of online learning? Like you do the model, and then how do you incorporate the data that comes the next night? Like you use the previous model and the next data, or the whole data up to it tomorrow?
So many of the observations don't really depend on the previous night's data. So there is a pipeline that does the regular cleaning and cataloging and so on. But when it comes to something like classification, yes, there is feedback that is allowed. So, but it's normally or not always done on a nightly basis. Plus, for some of the real-time stuff, we have pipelines that run during the night, but the next day at a more leisurely pace, there are pipelines that do a better job that also run. So you'll have two pipelines that are running. One, because you want something quickly out to see if something very interesting is happening. So it may skip some of the processes which may take a long time but may not be that critical. And right. And so there are entire networks of telescopes. So for instance, we issue something called alerts. So if there is an interesting target, then an alert is automatically issued. And there are telescopes that can be receiving those alerts automatically and pointing to that location so that they can quickly take additional observations.
I see. Okay, my main concern is that like if you use the whole data, like if you keep using the whole data, say every month from the time zero, then it's like huge complexity of the runtime, right?
So again, in methods, when we talk of these features, there are two kinds of features. There's one kind of feature, consider the mean. If you have a new data point, you don't have to calculate mean of everything, right? You have the mean, you can simply do an incremental measurement to do that. Whereas there are other features where you may need to use all of them perhaps. So online learning versus complete learning, you have to take that into consideration.
Plus for these surveys, you have to remember that at a given point where there's a candidate source, even at the end of the survey, there's only 1,000 measurements at the point. It's not.
Right, so you're not coming back the next night necessarily.
I see.
Right.
Yeah, if it is in the order of 1,000, it's okay.
So there are what we call the frequency or the way the observations are spaced is called cadence, and different science groups have different cadence in mind because the science they want to do is different. So for supernova, you may want to do frequent observations every 1 or 3 or 5 nights. But there are some binary stars where what you want is observations, if possible, every few minutes, right? So you may do, say, 100 observations within a night, and then do all what you want, and come back maybe several nights later and so on. So it depends very much on science. So there are also some deep drilling fields that have been proposed, like you observe most of the sky at a cadence of 1 to 3 or to 5 nights, but then there are some fields where you keep on drilling, you take large number of observations within a few hours. Or there is some where you want a cadence of, say, it's okay if I get one observation every month, because the variability is over a much longer period. So that adds a lot of complexities to the whole process. So some of this cadence related dealings between different groups used to be called cadence wars. They have now gotten a better term called cadence diplomacy. But if you have played the game diplomacy, then you know that it's much worse than cadence wars, right? So yeah, all those kinds of things, yeah. So you had a question, Eric?
Yes, it's not a good question in that it's a clear question addressing exactly what you said. It's sort of a vague question about an approach that I haven't heard the astronomers take, but it's a common approach in econometrics. And so, of course, econometrics almost always has evenly spaced data. So many of these methods can't be used. But the approach, I think, is worth thinking about. So what they tend to do is they have some time series with some interesting structure, and then they try to model the structure, and then they look at the residuals of the model, and then they say, okay, it looks great. I must understand it with the model. So the question is the residual analysis. What does one do when one has residuals? But you can do the same tests even on the original time series, and just ask, do I have something that approaches basically Gaussian white noise? Okay. So the question is, what are those tests? And it ends up, it's not simple. There's actually a slew of them. So let me slowly rattle them off. The most common ones that are known in all of statistics are tests of normality. Anderson, Darwin, come over, Smirnov. And that says, is whatever the values are do they just forget the time dependence, just the values? Do they have a Gaussian dependency? The next one might ask is there serial correlation? Are they sequentially random, or are they sequentially related to each other? So that's actually an independent question. You can have things which have a Gaussian distribution but have serial autocorrelation, or have no serial autocorrelation. Sorry. But are not Gaussian. You can have either they're totally different. So that's a very famous one from the 1950s called the Durbin-Watson test, and that one has an analytical probability, meaning for the null hypothesis that it is Gaussian white noise, they can tell you the serial correlation is 95%, 99% significant. So those are two classic things that one does. In this, I forgot, a few decades ago, Box, that's the famous George Box, son-in-law of R.A. Fisher, and his students developed tests for independence, that's the I in IID, okay, 4 time series, Box-Pierce and Box-Lejeune, and Lejeune-Box test. I quite don't understand the details of what's inside of them. There's a debate, something about Lejeune-Box is not as good as Box-Pierce. I don't quite know, but they're not perfect. Okay. But they test for independence. A different test, rarely used outside of econometrics, is the BDS test for IID, for independence and identically distribution. And that's from Brock, Deschard, and Scheckman for nonlinear serial dependence of time series. And then there's tests for stationarity. And this is usually a lecture in a graduate course in econometrics, okay, on unit root tests. Do any of you ever taken that class? Did you? Could you tell us about it? It's sort of a math thing, and if you violate the test, then you're non-stationary.
Right. Yeah, you're just basically checking to see whether the coefficient on like the AR, the autoregressive term, is 1, or I think the alternative is like greater than 1 or
greater
versus less. I think there's something special about exactly equal to 1, but you're basically testing is it greater or less than 1.
Right. And if it's greater than 1, it diverges.
Right.
And less than 1, it stays. It stays within, it has
And
autoregressive.
then the famous test is the augmented Dickey-Fuller test.
The augmented Dickey-Fuller test is the famous one. Also, the Durbin-Watson test, I'm sorry, I'm going back 5 minutes, is the test for serial autocorrelation. That means adjacent values. But the generalization is called the Bruce-Godfrey test, and that where you specify, let's say, 5, and it says, is the 5th one away? And you can do it for all sorts of numbers like that. So you're not limited to 1. Okay. So these tests are available and for testing sort of null hypotheses of evenly spaced data. So the question is, do they all collapse and are all useless for unevenly spaced data, or are some of them, sometimes can they be dealt with? So for example, the Durbin-Watson statistic is based on the autocorrelation function, but there is something called the slot autocorrelation function, which means the correlative function for unevenly spaced data that only fills in the values that are valuable. There's been no statistical work on that. Only physicists and astronomers use it, and I really would love some statisticians to look at the slot, or also called the discrete autocorrelation function. By the way, in astronomy, the astronomy paper that presented this statistical function has hundreds of citations, and yet there's not a single theorem in the paper. So we don't know. Is it good? Does it converge? Is it consistent? Is it,
You mean for the DCF?
for example? And so there is research that could be done on these various hypothesis tests of simple null hypotheses like normality and stationarity and IID and lack of correlation, which if we could generalize them for regularly spaced data, and if they work for sparse, well, some of the data is not so sparse. We can then give them to Ashish. And you could put them into your collection of characteristics.
Mhm.
And
Right.
As you showed in the one slide, you said, oh, I have 10 million, but only 10% are variable in any way.
Yeah.
Well, 90% of them may satisfy these null hypotheses. Well, they're just not anything. They're just not interesting. And that's not a useless thing for you.
Yeah.
It's
Even
nice
being able to say
to
that is
prove the
useful.
reliability of throwing away 90% of uninteresting things
Right.
helps you a lot.
Absolutely.
In proceeding further. So I finished my question, which is more a comment than a question.
But I have a comment just on
Yeah,
your
what do
comment
you
that a professor in our department, Kai Chung, he proposed a test of independence that doesn't make any assumption on the joint distribution in January this year. So just you can look at it. I heard a lecture of him.
Why don't you send it to me? I'd be curious.
Yeah, it's I'll send it to you.
Thank you very much. That'd be very sweet.
Okay.
Okay, someone else? Anyone on the astronomy? You must be confused by all these supernova type 2s, mirror variables. I mean, this must be terrible for you. I mean, it takes a whole...
Well, you don't have to remember all the names. That's why you
know,
always look them up.
The sky is full of weird physical phenomena that make things change, and sometimes go bump in the night. Events happen, and I think as statisticians, you don't really have to understand all of it. But
No, definitely
The
not,
more
yeah.
you know, you can ask questions. He'll tell you. What do you mean when you say these funny words? Like those funny words.
So in fact, related is one question that Tom asked during the break, that how do we deal with various things? So we also use the recursive partitioning, and we used in a paper a couple of years back, which started at SAMSI, by the way. So a few years ago, the group that we had, so Gillian Faraway was here, and we worked together on that. And so what we do is that you can have trees, decision trees that do the work for you. So you can have boundaries or cutoffs where you want the objects to be on one side and objects to be on the other side, and you want them to be probabilistic. And so what you can start doing is that you can say that, okay, the probability is low, so it's not that. So you try another branch of the tree, and the probability is low, so it keeps on going down. But what may happen is that after you go several branches down, you find that the probabilities are so low anyway that you have to go back to the earlier one. Maybe that is what it is. So we have multiple leaves that can have the same kind of object. I'm sorry you cannot read them, but let me read out this supernova, this is supernova, this is supernova. So when you start coming down the tree, depending on which features that you are splitting them on, they can go multiple ways, and each of them can have these multiple leaves that you have. And that is the kind of thing, but in smaller trees, that something like random forest uses, right? So random forests are very popular machine learning tool. They are ensemble of decision trees, so you take a few features, you take a large number of trees, and then they percolate it and find out which of the trees are better, and at the end you get a good classification. And they're extremely popular, they're extremely good. And so one of the first tests, especially in machine learning, that we do is that if your technique can beat random forest, then your technique is good. Otherwise, we'll use random forests. So random forests are that generic these days. We keep using generic forest. And so for specific things, though, there are of course many other things that can be better, like the Bayesian networks, right? I mean, you know about Bayesian networks as statisticians. You have the directed acyclic graphs, and this is a standard example that we have. So I'm going to show you a naive Bayes thing, one of the things that you mentioned earlier, Eric, today, that suppose I have a large number of these observables, and these can be the features that I have from my light curves, or these can be colors or magnitudes that I have directly observed, like J minus R, R minus I, I minus C, or other observed parameters or features, or there can be other incidental parameters, and all of them can connect to this class, because each of them, the priors that they have, that they lead to, connects to the class. So it's a naive Bayes when you forget about this connectivity, right? All of them are leading to a single feature there. And so I can update my class information, which is a multi-nodal thing. So all the classes are in there, so all of them lead to that. And the independence of that is what is crutch that I'm using. So long as the features that I have are mostly independent, then the naive Bayes may still work. If they're completely independent, of course, it's fantastic, but it's unlikely to be. For instance, when I use the G minus R color and R minus I color, they're not completely independent, but they're representing different parts of the spectrum in some sense, so they are independent.
So you put different priors in like each of them, you're saying?
So each of them will have a different prior, yes.
What if they're not independent? Could you put a prior on both of them jointly?
Right, so that is an issue, and that is why what you would like to do is try to go to fully Bayesian if possible, right, where you can bring in those dependencies and so on. But so really that is the aim, right? So you have a large number of nodes here, features, and your aim is a final constraint that tells you what all the classes are, where there are these multiple layers, not a single one. But as your nodes increase, the computation for that increases really, really fast, and you just cannot do it beyond a small number of parameters. And that is why what is useful is, if possible, if you can break this network down into smaller number of naive Bayesian networks, that's fantastic. And so one of the things that we did is make a supernova versus non-supernova classifier using just these 3 nodes. And the good thing about this is that it doesn't need any follow-up observations. So I take the position of the supernova. Using an archival catalog, I find out what is the distance to the nearest star. I use that as one of my features. I find out the distance to the nearest galaxy. That is another feature that I have. And that I have to use a normalized distance, because there can be multiple galaxies nearby. So if this is my transient here, and I find that there is a galaxy here, the galaxy is extended. So you talk in terms of how many radii of that galaxy your object is away. But if you had a more powerful telescope, and if you were to zoom into that small rectangle, small square there, you may find that there is another galaxy that is closer than that. And then you have to ask that if it is a fainter galaxy, then how many radii of that galaxy is your object away, and then you normalize according to that. So that is another parameter. And the third parameter is what then we define using a statistic. You define using domain knowledge. So you know that a supernova should have a single peak. It should not have a second peak, and most of the time it should be quiescent. So you take the total span of your time, you take the total number of observations, you can use some weight, and then you can just find out how many peaks that you have. You define a certain threshold, find out how many peaks you have. You can also see if there are connected points within those peaks, so that you can figure out the time span of those peaks, and then use that information to define a single feature that you can use along with these two. And we find that you can get 80 to 90% accuracy based on what kind of data set that you are using with these. So again, this is a naive network, naive Bayesian network that was defined using features that you have. This is again for a specific class, so this can be one of the nodes that we saw earlier in our partition tree. And then similarly, you can define additional ones like this.
These three identified in some automatic matter?
Yes,
based on the data?
right. So what will happen is that when observations during the night come in, you have a catalog. You have a position of each of those. So for each of those, you already have information about the nearest star, nearest galaxy. If that observation, that point was not looked at before from the catalog, you can figure that out. And then this you'll have to compute. So you have a new point now, you have an earlier light curve, then together you can compute this.
I guess what I mean is that, did you guys just think these three would be good and you tried them and it works well? Or did you have like a list of a dozen or several dozen and some algorithm identified for you that these three alone?
No, we had a few more, but it wasn't through an algorithm that we got this. This was more really through the domain knowledge, knowing what a supernova, how it should look, these should work, and they roughly do. And there's clearly a way to improve this further by improving on this. So for instance, if you wanted to separate objects with one peak versus multiple peaks, you may want to tweak that a little bit, perhaps to put out two different parameters. One is how many peaks there are, and one would be some kind of normalized number again.
Right. Like 1 equals could have two peaks.
Right. Yeah.
So if I could just comment on naive Bayes from 2 slides ago.
Mm-hmm.
So
You want me to go back?
whatever, sure.
Okay.
So I'm looking at a well-known paper by a computer scientist called a new explanation on the superb classification performance of naive Bayes. So the problem is this assumption here about independence, and that G minus R and R minus R obviously aren't independent, and so it shouldn't really work. But it consistently works extremely well in practice, and it's widely used for text classification, for spam classification, for many practical engineering social purposes. And so there's been a lot of statisticians who've been wondering why. So here's one, and I'm not the right person. It's full of theorems and proofs and definitions, which I don't understand. But this statistician says that this statement that they have to be independent is not quite right. That the dependence distribution, how the local dependence of a node distributes in each class, and whether that's evenly distributed or unevenly distributed, that determines the optimality of naive Bayes. And there's a much wider range of situations where it's optimal than what they originally thought when it was first formulated. So I think we should be aware of this continuing, I don't know if the word is debate or elucidation of naive Bayes, but the practical experience, just like random forest, has proved to practically be a superb tool for many classification purposes. Naive Bayes has proved to be practically extremely good. Also, the reasons have been widely described, discussed, and perhaps explained. And we as astronomers maybe should be more using it. It's extremely simple. It's
Yeah,
the
it is,
simplest
yeah.
of them all. There's no iteration. And it's also a soft classifier, right? When you do a decision tree, supernova, ends up in leaf, 2, 4, 9, and 12, and that they're there and they're nowhere else. And it's a hard classification. And if you make a mistake, it has some false positives and false negative mistake rates. Naive Bayes doesn't do that. It's a soft classifier, and it says, "Oh, do you want to know if it's a blazar or a supernova or a mere variable?" There, I got the vocabulary right. The probability that this particular object is 30% and 99% and 0%. Those percents don't have to add up to 100.
Right.
Okay, and so then you would say, well, it's certainly not in the third category, and it's most likely in the second category, but it's possibly in the first one too. And particularly when we have inadequate data, irregularly spaced, and also in Ashish's world and the LSST world, the data is going to come incrementally. We're going to start with, 20 data points, and then get 50, and then have 100 end up with 1,000. It's going to take 10 years to get 1,000. So what's going to happen, I think, what people I think is a good idea is to have these probabilistic soft classifiers that whose probabilities get better and better. So at the first, they say, well, it could be anything. And then as time, the data improve, it hones in, hopefully, on the correct classification cleanly. Well, if you force it into a hard classifier, you can have terrible data, and it will say, oh, it's a supernova. I mean, it's yes or no. It doesn't give you probabilities. You can jiggle the tree. That's what random forest is about, is to try to add probabilistic aspects to a hard classifier. But naive Bayes is soft from the beginning. I'm wondering whether we should just think more seriously about naive Bayes as a central tool, providing we can establish those prior distributions.
Prior distribution and coming up with the right features will be the important thing for
And-
any specific case.
And it's my personal experience with naive Bayes, which I have a little bit, is a big pain in the butt just getting the prior distributions of everything.
Right.
For each class, for each variable,
Yes.
you have to get the complete smooth distribution PDF.
But then on the other hand-
and a lot of that ends up to be guesswork in practice. You just sort of do your best.
Yeah, but you can
There
also
are
divide
two-
and win, right?
There are two priors in the terminology that
Yes.
are being confused. One is the conditional density of the features per class,
Yes,
which is what you're.
that's what I say. Right.
And then there are the priors. I mean, it's a Bayesian classifier. There are priors, which are the predominances of each class.
Right. So
Which also have to be.
Yeah.
I was assuming that was unity, there was uniform priors on the classes, but you definitely need the conditional priors for each variable. But you're completely correct. If you know that supernovae are 10 times more common than blazars, then you would put a prior on the class as well as a prior on all the variables as well.
Right.
So thank you again. That's
Yeah,
right.
that's
But
very.
it just strikes me as an easier world to live in than a lot of the other worlds.
I think there's an issue though.
There's no iterations, there's no computational problems.
Yeah, I mean, it's nice that it's a soft classifier, but I'm pretty sure the calibration of the probabilities is much more sensitive to the independence assumption than the performance of the classifier. In other words, so you run naive Bayes, and usually the performance measures are how often is it right in the
That's
sense
right.
of getting
False
the,
true.
instead of get in the sense of getting the highest probability class being correct. But then another issue is, okay, it told me the probability was 90%. Is it right 90% of the time? And I think that's actually not so good. And that tends, whether those probabilities have any kind of interpretable calibration is much more sensitive to the dependence assumption.
So my way, thank you, you said it much more clearly than I was going to say it. I was going to say one has to add an heuristic decision rule after you have these probabilities, because it doesn't tell you anything useful. It just tells you, oh, the probability of being a blazar or a Mira or a supernova is 0, 99, 30%. What do you do with that? And the answer is, well, you need a decision rule. So I'll give you an example of why that's not so trivial, right? So one is the one that Tom mentioned. You just do, take the 90%, that's the most probable one. But what if the most probable one is only 20% and the others are zeros?
Right, so we do
That's not
encounter
good enough.
that.
Then you maybe want to say, I can't classify this one at all. So you might want to put a threshold in there. And then another one that I like is to say, I'm only going to say that I'm pretty sure it's this class if the probability in that class is at least twice as big as the probability in any of the other classes, or else it's a tie. It could be 2 or 3 classes. And so how do I make up that rule? And the answer is there's no, it's heuristic. There's no rule to make up the decision rule. So if I were to say if there's a disadvantage to Bayesian, naive Bayes procedures in addition to mathematical issues, is the lack of clarity of making decisions at the end. Do you have a comment on that?
Yeah, so the heuristics do get used, so there are winner-take-all methods that sometimes used, or the 60-40 rule, that if it's over 50, then you use it, and if everything is less than 50, then you go back to the drawing table, keep it on the burner until you get something new, and so on, right? So yeah, but being naive Bayes, I think it is a good thing, and if we can identify the features, yes, that's definitely one way to go because of the soft classification.
But also, computationally, it's just lookup tables.
Yeah.
So it's extremely
Right.
efficient. If you have to do 40 billion of them
But again,
tonight,
you have
this
to-
might be a good way of.
You have to remember that the features will have to be not more than a small number of things
Let's say
if you
20
need
or
them.
something.
No, 20 is already, I think, still a bit large if you are dealing with too many things. So,
Okay.
yeah. So here's another thing that we use, for instance, for discriminating features. So what we are seeing here is percent of points used in a light curve, and how useful can that be to discriminate things. And there are two classes that are being used here. And so AGNs and flaring objects. So flaring objects are ones which have a very small delta t in which they really become bright and become faint again. It can be order of minutes, at most several tens of minutes typically. And AGNs are the stochastic ones where they just keep on bubbling and sometimes go up and then come down over much longer period, but always are doing a little bit here and there. And so if you take only a small fraction of points, then there is not much difference, but there is a certain time when you can see that they can differ a lot, and if you could pick them at that point. So these are again some boundary conditions that you can think of using. Okay, so let me go on to another one maybe, and then because all of them are similar. And so here, for instance, we are comparing AGN and CV, which are both stochastic in nature. And so, but the stochasticity is likely to be different. AGNs are active galactic nuclei far away. It is really a central engine in a big galaxy that is doing something, whereas cataclysmic variable is typically a star in our own galaxy. And then what we have done here is that we have computed certain features for only a fraction of the points. And we have tried various ways of taking that fraction. It could be the first n% or every nth point and so on. So if I were to take of one light curve, yeah, one light, or it could be a class, and that is why what you have here are the errors that you can have on them. So if you take a large number of them and you calculate the median value for all the light curves of that class and the boundaries, right? And so what you see is that if you take a certain fraction of points, you can start seeing how they differ in a particular feature. So the large number of features that you have, within that there are specific features for specific classes where you take fraction of points that is useful. Or here, for instance, what you have are AGN and supernovae, and standard deviation is used here.
I'm just trying to build intuition of this.
Right.
So it's saying that for many of these, if you use a fraction of the points, you get better discrimination power than if you use
Right.
all.
And that is because what happens is, take the supernova for instance, right? A supernova has a single peak. So once you are past the peak, you are mostly in the region where there is quiescent observations. So you are in some sense adding noise if you are considering everything.
So like 40%, you make the first 40%?
So in this case, it's the first 40% that we have used. But we have used every nth and so on, which is making it even sparser. And that was partly because to see if we can use some methods that are good for non-sparse light curves that we can use for sparse. But here, this brings it out more clearly for the supernova thing. So for a supernova, you see that the standard deviation is high when you take a fraction of the points. You have recently detected the supernova, so the peak is included. But as you go away, then if you're considering everything, the standard deviation goes down.
From the start of the burst.
At some point, yeah. Typically start of the transient phenomena, yes.
Well, this is extremely optimistic. Instead of running LSST for 10 years, we should run it for 1 year and stop.
But run it for 1 year at a differential time period starting from when you detect the supernova, right? Not the same 1 year. Right? So you have to know that a supernova is going off, and then
There is a problem.
so, and so what you can do is that you can use a large number of these to build something like binary brokers, right? You want to make a single decision. Is it of this type or not this type? And you have a small number of features. Again, this is somewhat like the naive Bayes, but even simpler. And then you want to ask that question whether it is this class or not this class. And then you have a certain set of features. And that is mainly because you need things to be done really quickly for a large number of objects as the observations are coming in. So there is the rarity determination is what is going to be crucial, and so use those specific features. And then what you can have is you can have a series of such brokers for different classes, and you can use various discriminators of the kind that I showed or what we have seen before, or you can stack the brokers in many different ways also. So you can have a broker that says C1 or not C1, another that says C2 or not C2, and the combination can be where you can stack them vertically one on top of each other, making a tree like we did before. But here the decisions are being completely independently done beforehand and then are being stacked apart. So this is more an issue of how you architect your system, how you try to build your system together. And the final combination of all of these, of course, is going to be something like this, where you want to find out what a fusion network is going to be, how all the probabilities are going to be combined together. Because some of these may be soft classifiers, some of them may be hard classifiers. That makes it difficult, of course, to combine them. But you want to normalize the probability at some point. So you can have an ensemble of KNNs or ensemble of decision trees. There could be a Bayesian network and a neural network, and so there's a data model that goes into supervised. So we haven't talked about things like the self-organizing map, which is a completely unsupervised model that we do use. So you put things in, and on a two-dimensional surface, it does a clustering on its own. But those kinds of classifiers are also there. There's the external knowledge like nearest star, nearest galaxy that can come in, or just positional information. What is the galactic latitude? So that feature alone was used for a long time to determine whether a particular variable is within our galaxy or outside our galaxy. So during summer, when you see the Milky Way, that is the disk of our galaxy, right? That is where our galaxy is. And so just like we have latitude, longitude on Earth, there is latitude, longitude, galactic longitude for our galaxy. And most of the stars in our galaxy are along the plane. So if you have large galactic latitude, that information alone tells you that it's more likely to be an extragalactic object. So that kind of prior information can also be used. So this, the area where one would like to go, and there are a large number of techniques that one can use. And this has not been completely solved, mainly because probabilities that come from different classifiers, it's not easy to combine them at all. So people try to do monolithic classifiers for that one reason, because you have probabilities from this method, probabilities from that method, combining them difficult. So if you have a good statistical technique to do that, or even connect ways of making those probabilities talk to each other, that will be great. The other important thing is when you want to extend your observations. So suppose you have a good soft classifier which tells you that of the 10 possible classes, you have eliminated 8 classes, but these 2 are still likely, going back to the example that we saw earlier. How can you disambiguate that information? So this is our distribution. So this says that maybe it belongs to this class 1 or class 6 or class 7, and the other classes have a low enough probability. And then you need a follow-up observation. So this is one telescope that you have access to, and this is another telescope that you have access to. And each of them, say, has a different filter, or one has a different kind of observing mode. The size may be different. There are so many different things that can be happening. So if you were to do observation with this telescope at a given time, it's going to disambiguate the observation, say. You can calculate that probability. Whereas if you observe it with another telescope at another time, the probability is still going to be ambiguous. So of course you have to go for that. But you can build a Bayesian network for that and keep that ready. So as the observation comes in, those get fed in, you can figure out. In fact, David has been working on using some basic functions for that. And this is a fit example. This slightly older slide from him. He has made more progress since then. So here, for instance, what we have are 2 different models that seem to go along reasonably well. The other models have been ruled out. They don't do well. And these are the 2 models. And then you ask the question that after this, when should I do one observation to disambiguate the 2 models? And then so you can extrapolate the 2 models, assuming that there are observations that are happening. And this gives you the separation between the 2 models as a function of time. And you see that this is the time when the difference between them seems to be maximum. So if you do observe them, then you have a better chance of disambiguating the 2 observations. So that's the kind of thing that will also be required a lot as we go ahead, provided we can bring it down to small enough numbers. We have reasonable probabilities for a small enough number of models there. Then the SOM that I mentioned earlier about the unsupervised way of doing clustering. K-means is, of course, another way that you can do. So if you have a large number of features, a large number of objects and a few features that you're looking at, and then if they are spread around in those 2 dimensions, then you can use K-means to figure out if there are n number of or k number of clusters in them. So what you would do is that how many clusters there are, you have to give that as an input. Of course, you can use a series of them at some point. And then in this method, the k cluster centers are randomly guessed. So they would be put somewhere, and then associate each data point with its nearest center, a fairly straightforward thing to do. And then you change the mean of the cluster. Now that you have determined it, it can be moved around, and then you'll iterate until some convergence criteria is reached. So that tells you how many clusters there are likely to be in the method, a fairly straightforward method. The good thing about k-means is that it terminates. So after a few set of iterations, it'll stop. So let's look at an example, in fact. No? I need to come
Are you
out of that.
doing them, all of them over the time, or
Sorry?
I'm trying to figure out how you would bring the time dependencies here.
What do you mean by time
Through the
dependency?
features that he selected.
What's that?
The features that he's classifying in are built from the time dependence.
Okay.
So like one of those features.
Right, yeah. You have converted the time series into features, right? And it's those features that you are using. Okay, so I need to move the...
So just maybe kind of quick, but so the number of features, the total number of features you talked about is now like starting to be the order of magnitude of the number of points in the time series. But
Yeah, it is, right?
So each feature is the kind of time being, or what?
It's based on the time, like a period comes from the time series, right? So it tells you something. It depends on it being a time series, but it's one scalar that tells you something about the time series. And he's giving you all these other features, these sets and statistics and differences and things like that. Those are all measures of something about the time dependence. Each one measures something different.
Yeah, consider the mean, right? The mean is a feature that you get from the entire time series. Similarly, standard deviation is another one. And if the mean and the standard deviation, those are direct inputs to the stationarity of the time series, right? Just by looking at those two numbers, you can say as a function of time, whether it is stationary or not, roughly. So similarly, you can use all these features, and we are now talking about various things, various operations in that feature space. So that is what when I showed you the picture of capturing the lion, right? So we cannot capture the lion, so we convert the problem into a simpler or a modified version of it, and that's what we are trying to solve. So here we have got 300 points, and we defined our number of clusters to be 5. So we have got 1 here, and these are randomly chosen. So 1, 2, 3, 4, and 5, right? So there's nothing here. So a large number of those, because you associate them with the nearest center, will get associated here. A very large fraction will get associated with that. Hardly anything will get associated with this, and then intermediate. So let's look at that. First step, this is what we get, right? So this happened to be the nearest to all those there. And where's the fifth one? Oh, the smallest one is here, right? But because this extends all the way up to here, this mean is somewhere here, I guess. So the center is now going to shift there within the next iteration. So you see immediately it shifted there. And then again, this is a long one, but the mean could be there. So there may not be, let's see how the changes happen. Some changed, and a few more changed, slight change, and a few more, and a few more. Fairly dynamic, but I think it'll end up being 5 clusters that we wanted.
The blue one's eating away the purple one.
Yeah.
Kid's greedy. He's gonna win.
Okay, I think it's
You're right.
converged, right? Done.
And this
So-
depends a lot on where you started with your initial 5 points.
Oh, no, it doesn't.
Kenny does.
So like if you had your 5 points on the left side, those close.
But it's iterative, right? It'll keep moving until
No,
it
but
adjusts.
K-means you're supposed to iterate it to get a solution, and then you're supposed to iterate again with different
Yes,
starting
yeah.
points.
So if you start with different centers, it is going to be different, but it is a good approximation what is. What we saw was that the 5 centers did move away. So they won't stay there, for instance. It won't be that they will be very uneven.
Right.
So individual members, yes, depending on the centers, things are going to change around.
But then it's like random forest. You have a forest of solutions, and then you have
Yes.
to decide what to do with the forest.
Right,
Um,
right.
um,
So it didn't like that.
I think
yeah.
k-means has some theorems behind it that are favorable. And whereas other methods, K and N type stuff with no theorems, they're just procedures.
So this is how it'll keep on moving about and going on. Okay, let's go back.
I think k-means is extremely rapid, so it's really liked for, image processing problems in engineering world.
Okay, so now let's look at some of the things that are starting to happen about now because of the large data sets and especially multiple data sets. And so the issue is not really being able to use a single data set like the CRTS or in the future LSST or some of the other things, right? But we should try to find a way so that we can combine all of these. And again, if we can use the time series or the features that come from them holistically, that'll be fantastic. So what I'm showing here, for instance, is the DASH survey, which is not a single survey, but they collected photographic plates from all kinds of places going back more than 100 years, and they have digitized those. And they are not as many as some of the newer surveys, but what we have is very important history. So we can build time series that go over a long period with larger error bars, not going as deep as the current surveys do, but still very useful information. And so then we have CRTS, PTF, ZTF will be coming in the future, PanSTARRS is another survey. There are many amateur astronomers taking data, also some other surveys. There are many surveys that are not mentioned here, by the way. The whole zoo of surveys is far bigger than this. And then it's the LSST that's going to come. And we are showing here, of course, just 2 dimensions. So there is time here and the brightness here. But if we could find a way of combining those surveys using the time series that we have from these different ones, that'll be a fantastic things. So one of the ways that can be done is using domain adaptation. And what we do in domain adaptation is try to figure out how essentially the features from one survey and features from another survey can be combined to get that information. And so we know that surveys differ in depth and filters and cadence, and same type of objects actually, depending on how your survey observations were spaced, produce different statistical features. So some of them, like mean and so on, won't change much, but depending on the cadence, some of the other features can change a lot, and I'll show you an example of that. And so typically in machine learning or any domain itself, the learning gets to be done, typically happens on a single survey. You don't see people combining multiple surveys and doing it simultaneously because it is difficult. Learning even on a single survey, machine learning tends to be difficult, non-trivial, unless you have very large data set, very good data set, and so on. And so the DA helps, the domain adaptation helps build them together in some way. So let me show you an example that we made using PTF and CRTS features. So PTF is a survey done from Palomar, and it has 2 filters, and it has been going on for a few years now. So these, it's all right if you can't read them. These are exactly the features that we were looking at earlier, the ones that we got from the time series. And when I look at PTF features versus PTF features along the diagonal, we do see that they're correlated as they should be. Off diagonal, there is less correlation, indicating that there is some kind of dependence that they may have on each other. Similarly, CRTS versus CRTS, yes, they're correlated along the diagonal. But I look at the CRTS versus PTF features, and I see that there is no correlation, or at least no strong correlation along the diagonal. And this, despite the fact that I'm looking at the same set of features for the same set of objects. So it's not as if I'm comparing apples and oranges. I'm, at least so far as objects are concerned, I'm comparing the same thing, objects and features, and still I don't see anything.
So within the the survey, what do you mean when you do the variant?
So this, what happens is that what I have, there are features here and the same features are here, right?
And are you looking at
So it's self-correlation when I'm looking at the diagonal.
for different, you have different light curves this?
No, so this is a set of light curves for a set of objects, right? So it's the same set of objects. So, okay, let me show you, this is the same sample of 50,000 objects that you are using. There are multiple classes, right? So if you take a class of objects, all objects in that particular class, and then you derive the features for them using CRTS versus PTF, right? So when you look at CRTS versus CRTS, you're comparing two numbers with each other, right? It's identical numbers, so they're going to be correlated. Whereas with PTF and CRTS, you don't get similar numbers.
So just the bottom left quadrant, so what you're saying is that you might not neatly expect there to be a sharp diagonal.
Exactly, because we are trying to compare two similar
And do
things
you
with each other.
Understand, like to first or zeroth order? Is it just because one has two filters versus open?
No, not just that. There are additional things like CRTS is over several years, PTF is over a shorter period. That is one, the size of the telescope is slightly different, and even within the years when there are observations, the spacing is very different. So with CRTS, you have those clusters of 4 observations and then something else, whereas in PTF, it's more varied than that. That's one of the reasons, right? And so what you'd want to do is, if you're looking at only 2 of those 20 or so features that I showed you, you can expect that in one case, if you're looking at the same 2 types of objects, you will see a line that separates the 2 classes this way perhaps. But in another domain, consider this as PTF and this as CRTS, you'll have the same 2 features. There will be a separation of the 2 classes within that particular survey, but the slope you may get is somewhat different. And that is because the features that you calculated were somewhat different. And so what this domain adaptation tries to do is find out a mapping between this and that. And of course, not just in 2 features, but in multiple features, right? So it's like multidimensional space in which you are trying to figure out some kind of a plane.
One of those plots for each survey, and it's trying to learn all those slopes?
So you'll try only 2 surveys at a time.
So there's feature 1 versus feature 2. Oh, source domain is one of the surveys,
Right,
and target
right.
domain is the other.
Yeah, this is one and this is the other.
Does it matter that one is called the source? Is there?
It would matter because it will depend on whether one has larger error bars, the other has smaller error bars, how we are doing the learning. So one of the ways you try to improve the learning is add a small fraction of objects from the better or newer survey to the older survey and redo the learning. So the set that we are using here is the 50,000 variables from Drake et al. These are the classes. It's a very unbalanced set. So that is another important thing to keep in mind, that you have to do something about the unbalancedness. You may not want to use classes that have very, very few numbers. So you use the classes which have at least a certain threshold of objects. And even within that, when you do the training, you find ways to make sure that you can balance the 2 sets. So one way that we do that is using something called smooth sampling with replacement. And so you have got these 2 features here, and what you can then do, you can see that there are far more number of crosses than number of circles. So you want to increase the number of circles rather than simply repeating some of them and inflating the number of circles. You pick, say, 3 of them, find out some average of those 3 and put a new circle there as if that's your new object. So that's one way of inflating their numbers, which is far better. So these are the few classes that we are using there, and that shows that we can get a better learning from there. So I'm going to skip the geodesic flow kernel. Okay, the codomain adaptation. So this is the diagram that shows how the accuracy can be improved. So here what has been done is that you take a small fraction of numbers of candidates from the target domain, add that to the source domain and do the learning. And as you add more and more data from the target domain, you see that the learning on the target domain starts improving. And this is because what's happening is that earlier, if you were learning only on the source domain and use your target domain as your testing, then you're not going to get things correctly because of the mismatch between the 2 feature sets. But as you start putting in more data into the source domain from the target domain, that is going to keep on improving. It still doesn't get to 100%, but whatever incremental improvement that you get is far better than not getting that. And this is especially useful when you are going to start a new survey. For instance, now ZTF, the Zwicky Transient Factory, is going to start at the same place where the Palomar Transient Factory has been operating. That is, the ZTF is going to have bigger chips and it's going to cover a bigger area. So in principle, if we go the way we have been always going, we'll have to do a brand new training on the new objects that we get from ZTF. So it will take about an year before we can get large enough data set for training and then accurately predicting and so on. But if we can leverage the PTF data, then we can use the 5-year PTF data plus a month or two of the ZTF data and already start doing better predictions with that. So that's another technique that's upcoming. And a lot of things are happening here within SAMC and at LSST, which I'll quickly go through in the next few minutes, and then we'll take a few questions and then stop. So there are 5 working groups that are currently happening in the 1-year program. Working group 2 is one of the programs that we are in, and a large number of activities are happening there. So some of the things that I mentioned, like the supernova feature, designing new features, that is one of the subgroups there. Then scheduling observations, David here is involved. That's also one of the subgroups. There's also one on outlier detection. We started talking to Tak recently about that. And domain adaptation is also a group. Light curve decomposition, I didn't talk much about things like karma and Arfima, but I suppose you already talked a little bit, and more of that will be coming in.
Not yet.
Okay.
It's coming up later in this lesson.
Right, okay. So I have one slide maybe on that, but we'll come to that. So lots of different things are happening, and all these are cutting edge, and if you people are interested, you should get involved in some of those. And there's a connection to the LSST community that is there, because many people here are also involved in the LSST working groups. LSST is open to anyone who's in the US, so that's another area where you may want to get involved in. And it seems slightly far away, 2022, but a lot of things are taking speed now. Simulations are already there and so on, so a very good time to get involved in.
And if I could just interrupt, LSST has both science collaborations on variables and transits, like variable star science collaboration, and also a science collaboration on information and statistical statistics and informatics.
In fact,
and
Tom is one of the
and Tom is the
co-chairs of
president
that.
of that at the moment.
And many of us are.
And the point being that, once again, to echo what Ashish just said that LSST is basically needs expertise. Young statisticians are very much, and astronomers are very much encouraged to join in on LSST preparations, including advanced methodology.
Right. So you're graduate students, and 5 years from now, you'll be, if you're involved now, you'll be in a very good position to do some leadership roles at that time. So
Your professors don't know this.
yeah. So we have been doing variability-based searches for quasars too, and we have managed to find large number of them. In fact, it is through that we found several pairs of black holes going around each other. And again, it was simply based on going after the features and looking for variations, periodic variations in them. And this is my only slide on these things, where we can look for non-stationary processes and long memory processes and so on. And I'm not an expert in this, so I won't talk more on that, but Eric says that it's going to be covered later on, so that's great. And then some of the other things that are happening in LSST land is there are a large number of simulations, though there is no real data. And so there's an operation simulation. So what that means is that LSST is going to take data for 10 years every night. So what the operation simulator does is that it simulates observation of where LSST is going to observe, use the air mass at that point, use the moon's phase at the time, and then it tells you how the data are going to look. And if you can input one of your variable objects, then how that variable object will look to LSST, you can get that. So you can get the time series of 1,000 points, and then you can do additional statistics on that, exactly like we've been talking. And so there is something called a metric analysis facility. Metrics are just numbers. You can ask that, tell me what is the average air mass for such and such set of objects if I provide you the RA index or something like that. And so you can get these metrics for a large number of these questions that you can ask. You can ask fairly complex questions. And the questions are asked of the existing simulations. So there are a large number of simulations that are there. So there is a baseline cadence that is there, or the universal cadence, or something like the pan stars. So the base cadence involves visits in pairs. So you go to one location and a little later you come back to the same location. That is because you want to find out if there is an asteroid that was passing through. And as I said before, you need to catalog all the asteroids so that when you come back and see the asteroid again, you know it is an asteroid and you don't worry about thinking it of as a transient and so on. But these large number of cadences are already there, and you can use many of these. So this is where you can ask really interesting questions. If you had 1,000 observations within 5 days, what can it tell me more than whether the 1,000 were distributed over 10 years? Or if I had 100 today and 100 1 month later and 100 1 month later, 1,000 within 10 months, how can I improve my classification for a given class of objects? So those kinds of questions can be asked now. And there are a large number of...
Very urgent, actually.
Yes.
To be settled, like, within a year.
Yeah. So that's where the cadence diplomacy is happening right now, right?
If you're doing features, the type of features that will be relevant.
Because of the cadence.
Yeah. Then there are a large number of subgroups within our transients and variables collaboration. You see a fantastic diagram that my co-chair Federica Bianco made from that, how the collaborations have commonalities with each other. So some high-level D3.js thing. So each person, for instance, tells you what the main area of interest is, but also 3 sub-areas of interest, and it's simply connecting those with each other. Okay, so this is my summary for today. We want to characterize and classify as much with as little data as possible. Only a small fraction of the objects that we find as variables are going to be rare, and we need to be able to identify them quickly so that we turn our precious telescope resources to those objects rather than the 99 or 99.9% other objects which are also variable but not as interesting because we know enough about them. And we have a variety of parameters. More are being identified, and we need to choose judiciously, so dimensionality reduction becomes very important there. Real-time computation is required. We didn't go too much into machine learning today, but that is a big component, and connecting that with statistics is a crucial thing. So finding ways to make that happen. And meta-classification is very important, combining the different classifiers, how we can do that, right? So this is where I finish the talk itself, but I want to go into a couple of slides where I want to mention about a data set and some R methods that we have that you may want to use, and maybe after that I can take questions. So I already mentioned earlier about the DTW cluster, which uses dynamic time warping. So this is something that you may want to try, and it has not been known to work very well for sparse series, but you could use some of the denser series and see. No one has tried that for astronomy as far as I know. And there what you can do is that you can look for similarity between light curves. So you can essentially cluster light curves themselves rather than features extracted from light curves. And so that may be a direct method about on comparing. So that's one of the things that I want to mention. The other thing is that the paper that I mentioned, the Faraway et al. Paper. So if you go to this URL, there are all our data that we used in the paper is available there, and also the code that we use to do whatever we have presented in the paper. So it'll be worth reproducing, but also see if you can extend it using additional data sets like the one with 50,000 objects. And if you're interested in using that, let me know. So what we do in the paper involves exploratory analysis and Gaussian process regression, which I didn't talk about today, and derived measures and variable importance. So we can quickly go to that. So I have one more slide which simply has a few references which you will have available later on. But so let's simply go here now. If I can click here, and it should take me to this. Okay, so this has the data. There is a link for the data can be found in the R database here. So the data is linked from there, and we have got various things that we did, R markdown scripts and so on. So you should take a look at that. I'll have the link for this. It's in the video, of course, but I'll also it's also in the slides, so you can take a look at that. So with that, I would like to stop and ask you if there are any questions. Let's see. Where did my slides vanish? They're gone. Okay, back for a second here.
Okay, are there any comments or questions?
I have a question. I mean, I think you
Tom.
kind of alluded to this one. So you talked a lot about classification, and you briefly talked about clustering, and you mentioned outliers. But so the question is related to those: is that what is the formal way you guys are thinking about serendipitous discovery, finding things that we don't have a name for yet?
Okay, so that really comes from one of the earlier questions you had too. If you keep on looking at probabilities of everything and then you find that it doesn't fit into anything, there will be a separate bucket for that. And those would be the rare transients. So in this broker thing that I mentioned earlier, right? About here somewhere. All the way back. Okay, this one, right? So when we talk of these rare transients, these are either the ones that we know very few examples of, or the ones that we have not been able to classify. And so people will be very interested in that. And the way the whole thing is going to work, and Antares is going to be just one of the possible brokers. There is space for 3 more brokers to come. And so this LSST pipe will be really a data hose. There will be 10 million transients being sent out every day, and LSST itself does not have funding to do the classification, and it is up to the community to do that. But NSF is ready or will be ready. There will be ways to get those things funded. So someone who receives all those and is able to classify, that'll be a fantastic service and work will be done. So something like this, and that's where all those interesting transients will be, and people will have ways to ask questions of the service.
So I guess what I'm wondering is there a way to try to quantify whether the problem of having this high entropy posterior over the classes is just that you don't have enough data, or is it because it's really something different? Those are 2 different things that produce a high entropy posterior.
Right. It is a difficult question. So just given the number of possibilities that are there and the very little data that we have, and within that, whatever is being done are trying to put small portions or fill small portions of this diagram. But again, good methods on the existing data will go a long way to help with that.
In the naive Bayes sort of framework, I think that problem doesn't arise. If you have very little data, let's say there's 5 characteristics, you have terrible information. Let's say you have 3 categories: supernovae, blazars, and CVs. Okay. Well, the probability that it's a supernova is 90% because it is so little information, it fits any supernova. Well, it also fits any blazar and any CV. So it's 90%, 90%, 90% in the 3 classes. And that's when you have terrible data. And that's very different than the situation where you have excellent data and you say, well, does it have the characteristics of a supernova? No. 0% for supernova. 0% for blazar, 0% for CV. Then it becomes a rare transient. So, although one doesn't have to use naive Bayes machinery, conceptually, that same concept should be there in other procedures as well.
But also here, right, meaning there may be some objects that we don't know many about, and if the characteristics indicate that it may belong to that will also come through rare. But because it is rare, not many of those will be rare of the 1,000 that we get every night, right? So.
Again, back to the features that you mentioned and time dependency. Is there any way we can look at the features over the time and then eventually project them on 2-dimensional?
So this is what, sorry, this is the wrong one. This is what we meant by features, right? So you have a single series here, right? And you abstract that into many different things. So amplitude becomes one feature, moment becomes another feature, periodicity becomes a third feature. So you are essentially making this large number of numbers from this single time series.
But it sounds like what you're thinking of is features like that, but that are localized, and then asking how they evolve along in time.
Yeah.
Right. So the other thing that I showed you is something like,
And then
Yeah.
eventually the goal is classifying probably.
Right.
And you can project them on the two-dimensional sea.
you don't have to project them if you have a good method that can
Oh, yeah.
give you a probability. Yeah. So something like this is exactly that, right? What I was saying is that you're considering only n% of points from the entire time series that you have. And so you calculate your feature for these many points, you calculate them for these many points, these many points, and that is what is now plotted here. So this is even the lower order or next level kind of set of features. And I've computed that for 2 different classes. And for one particular feature, what is the standard deviation for this time series and standard deviation for that time series, and I have plotted those. So isn't this what you're asking then?
Yeah, I know.
Right, right. So yeah, we have been doing that, and more can definitely be done. And it can be, as I said again, you can also take every nth point as well, right? Or then you can figure out what are the peaks and then take so many points around the peaks versus so many peaks around the trows. Or there have been some smoothing functions where you drop the 10% of the lowermost points or 10% of the topmost point and then compute something, right? Because then that's reducing your outliers that may be spurious perhaps. So things of those kind.
Could you go back to a slide you just showed that had amplitude and moments and a couple other broad classes of statistical measures?
Which one? That
Uh,
was the one that was a generic one?
It was generic. It was just, well, it had amplitude and moments and periodicity. Those were the 3 that were listed. What I'm
This
sa-
one?
Yes.
Right.
So those are broad characteristics of which there can be individual measures, maybe even multiple measures.
Right. Yeah.
Could I suggest, I'm not saying this definitely, suggest for thought, that 2 more come to mind that are broad concepts that are not those 3. One is the concept of stationarity,
Mm-hmm.
so that whatever the behavior is in year 1, it's the same as in year 3 and year 5. It could be a periodic variable, it could be constant and totally uninteresting, and it could be stochastic, but it's the same characteristic. And that's what stationarity is about. Some things are stationary, some aren't. Stars and galaxies.
Mhm.
The other one that comes to mind is autocorrelation. And I'm not sure that's so useful because almost all interesting behaviors are autocorrelated. So I think just saying, oh, it's autocorrelated just means, well, it has some behavior that's not random. So maybe that's not so interesting. But certainly what the autocorrelation function measures is the nature of the autocorrelation. And one could both do hypothesis tests on it and one could do some sort of characterizations of it. And one example is long memory autocorrelation, which is
Yes.
separate from short memory correlation. Astronomers call long memory, or an important class of it, as 1/f noise. And that's not a trivial issue. I don't know if LSST data is going to be good enough to,
Right,
to
but-
pull that out. But it's the concept is a concept of what's the nature of the autocorrelation.
So in fact, that is being explored even using machine learning. There is something called the LSTM, the long short-term memory.
Really?
Yes, and so what you do is that it's a kind of neural network where you can even take irregular time series and then each individual point becomes an input, and then you have all these, something like gates, but probabilistic things where you can combine things and so on.
That could be really useful for this
Yeah,
stuff.
so there are groups that have been exploring that. So I had to leave out a
Computer
lot.
science groups or astronomy groups?
Astronomers are involved.
It's not it's not limited to time series, it's like in images too. It's kind of local versus global.
Right, so in deep learning, for instance, that get used. So it is a kind of recurrent neural network that uses that.
So do we have the computing capability of doing neural networks every night?
Oh yeah, yeah,
We do.
we do.
We don't have to just do single pass
Right.
calculations. It's only 40 billion, it's not, it's only 10% of 40 billion. It's not,
Yeah. And yeah, as I said, I had to leave out a lot from here. There are many groups that are doing small things. For instance, the unsupervised clustering, I didn't mention too much about it, but people are doing those things as well.
This actually raises an interesting question. There's this emerging area of statistics that worries about resource expense as part of designing an algorithm.
Yes.
Is that anything you guys are looking into? Like that, that there might be some kind of hierarchy of fidelity of classifiers or something?
Yes, that has to be considered, because a fantastic classifier that will take ages to run is useless, right?
That's right.
And so whatever can be done quickly, and that is when I mentioned that there is something that will be running in real time, which may not be the best classifier, but that will quickly do the job as best as can be done, and so the alerts are pushed out. But during the next day, when all data have been taken for the night, then there will be better methods which need longer, which need more computers, will be doing things that go with it. So that is always in the back of our minds when these things are put together. And not all the work has been done, not all the thought has gone into that, but it's there somewhere.
So this is, an example of that kind of thing. It's in astronomy. It was an astronomy problem, but it's published in the statistics literature. But John Rice was involved in this. And it's not classification, but it gives you an idea of the algorithm. It's of the kinds of questions people are thinking of. They were looking at period detecting a periodic signal in arrival time series, not sample time series. But and they designed an algorithm that uses dynamic programming that says, okay, there's no way to exhaustively search all of the period space, but can I, specify the maximum number of resources that I have, and an algorithm will tell me the optimal way to kind of coarsely resample that gives me the highest power for that given resource expense. And they worked out how to do this.
Yeah, that'll be quite useful.
It was the first thing I ever saw that tried to do that for me. I think that's going to be a really important new area of statistics.
I'm amazed at the complexity of what you tackle, Ashish. I
It is
congratulate
complex,
you
yeah.
for keeping it all in your mind and aiming towards the future here.
Well, shall we formally
Okay,
end the class?
it is now 7 o'clock. Oh, you ended 1 minute early. You're better than me. Okay. So any comments from the students? Everything okay? See you next week. This is the first. We now have 2 coming up on planets. And then, 4 visiting researchers on planets. And then we have spring break. So I will be here next week. And then, unfortunately, I will not be in the room for the next few weeks until after spring. Okay. If you have one of you has handed in your first assignment. I'm looking forward in the next few days for other first assignments to arrive. Any questions you have about the class, go to me. Meaning, I don't want to, the word hassle is not the right thing. The visiting lectures are not responsible for the class, honestly.
And if you have questions about the data sets or would want to try something out, let me know.